AP Chemisters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. So we begin with section 8.7. We're talking about ions. And with this, we're going to look at the electron configuration, the magnetic properties, ionic radii, and then the ionization energy. So very important section. Plan on seeing something on the AP test, either multiple choice or often a free response question from this section. So first of all, let's talk about electron configuration and making the ions. For your nonmetals, your anions, as you might remember, the anions will gain electrons to fill the outer shell. So if I looked at fluorine, oh, by the way, when you're doing this, have a periodic table handy. If you need to pause this and find your periodic table, go for it, but make sure you have one to look at. So if you look at fluorine, you'll see it has 9 valence electrons. So we're going to start from the beginning, 1s2, 2s2, 2p5. And what we're looking for is it's going to gain an electron to fill the outer shell. So if you look at where fluorine is on the periodic table, it only needs one more electron to be like a noble gas. So your F minus be 1s2, 2s2, 2p6. Notice if you add up these numbers, 2 plus 2 plus 5 equals 9. 2 plus 2 plus 6 equals 10. So the fluoride ion has 10 electrons, still has only 9 protons, and you notice the overall charge is -1. What will metals want to do? Cation ions are going to lose electrons. Why will they lose electrons? They're going to lose their valence electrons to have a filled inner shell. Then you're going to lose your outer shell electrons, so you have a noble gas configuration once again. So lithium has 3 electrons to start off with, 1s2, 2s1, but which ones is it going to lose? Well, it's going to lose the electron that will then give it a noble gas configuration. So the lithium plus is just going to be 1s2. Again, like I did before, if I'm going to count my electrons, I have 2 plus 1 makes 3. But here I just have 2 electrons. So I have 2 electrons and I still have 3 protons. Look at my overall charge, it is still +1. For aluminum, as you know, is an always, it is always going to be a +3. Go ahead and you do this, see what you get, pause it, and see how you do. Okay, so hopefully you got this. You have 13 electrons here. So 1s2, 2s2, 2p6, 3s1, 3p1. So again, your S and your P metals, not your nonmetals, your metals are going to lose so that you have a noble gas configuration. So we need to lose all of those. I'm sorry, there's a boo-boo here, isn't there? Put a 2 there. So now we get 1s2, 2s2, 2p6, and that is your noble gas for neon, or electrons of a neon. Here we have 10 electrons, 13 protons. Look at your overall charge is still +3. That works. So what do we do about transition? Transition, as you know, I call wishy-washy because most transition metals, all but 3 of them, you can have a variable charge. It can be +2 or +3, +1 or +2. And so how do you know what it will lose? If you think about it, almost, not all, but almost every single transition ion has a +2 ion. All your common ones, like your copper has a +2, your iron has a +2, even vanadium has a +2. Why is that? Because transition metals in D block will usually lose their S electrons first. Okay, a couple exceptions, but that's pretty much the rule. And this is true for F block too. We hardly ever look at F block. So if you look at vanadium, we have 23 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then watch, 3d, 1, 2, 3. So if you add up all those electrons, yes, you get 23. But which ones are you going to lose? You're going to lose these. You're going to lose your S electrons. So you end up with 1s2, 2s2, 2p6, 3s2, 3p6, no 4s at all, and then 3d3. You don't really need to put a blank there. But if you were to count all these electrons, 2, 4, 10, 12, 18, 21, this has 21 electrons, 23 protons. Notice what your overall charge is. It is going to be a +2. Now, is that the only charge that vanadium has? Of course not. Okay, but that's the most common one. You're going to lose those s electrons. Let's go to the next page. Okay, so there are exceptions. Do you remember what we said about silver? Silver's charge is always +1. As it also turns out, copper can be +1, which is above silver on the periodic table if you look at it. Gold, which is below silver, can also be a +1. Why is that? Why is that particular column in the D block prone to have a +1? Well, let's look at the electron configuration of just silver. I hope you don't mind. I'm going to go and do the noble gas configuration. So I need a krypton here. Okay, and then after krypton, looks like, what is that going to be? 5s and 4d9. Okay, so if I were to go ahead and do this, watch what happens with the orbital notation. I'm just going to do this. And there's 9 electrons. Up, down, up, down, up, down, up, down, up. Okay, so that's what a silver atom, a neutral atom, will look like. But you may or may not recall it being said that there is stability in a filled and a half-filled shell. Okay, so we got to be really careful because you typically do not promote between the different energy shells. But if you go back here, let me pause this for a second. If you go back, I think this is like maybe the second page or something, and you look at this energy scale here. And once you get energy shells that are really, really, really close to the same energy, look how close that 5s and the 4d are to having almost the same energy. It gets a little murky, and you can't have these always statements anymore. Certainly it's going to, this is a much larger energy jump, probably not going to happen. This is a huge energy jump. I doubt if that would ever happen. But look at here. Here's your 5s to 4d. That doesn't take a whole lot of energy to go between the energy shells. You're only going up by a little bit. So let me pause this and go back to the page that we're on. So we're back here again, and look what can happen. This electron right here can be what's called promoted. Okay, it's going to go to that 4d shell, and look what happens once we promote this. Very, very stable. We have a filled shell, and we have a half-filled shell. And that does have a very stable configuration. So silver in particular will promote its s electron to that last 4d shell to have it a filled shell and have a half-filled shell at that point. So this is probably the most common configuration, or more stable configuration for the silver atom, the neutral atom. So when we talk now about the silver ion, what are we going to do? Well, what did we do before? We took out the s electron, but in this case, how many electrons are in its s shell? It's only one of them. So your silver ion has krypton 5s1, but wait a minute, that's the one that we took out for D10. So when you have a silver ion, you do not have that 5s anymore. You remove that and you are left with 4d10. So if I were to rewrite this, maybe I'll do something like that. My final answer is krypton in the brackets 4d10. What can we do at this point? Let's add up our electrons. So krypton has 38. Plus 10 more makes 48 electrons. If you look at silver's, it has 47 protons. Wait a minute, that doesn't work out. Well, silly Mrs. Vanderlei, I can't count, can I? Krypton doesn't have 38, silly Mrs. Vanderlei. Krypton has 36. So 36 plus 10 make, here we go, this makes a whole lot more sense. 46 electrons, 47 protons, and that is going to be a silver +1 ion. Now we have two terms that talk about the magnetic abilities of these atoms and their ions. Paramagnetic is if you ever have an unpaired electron. So guess what? You need the orbital notation to really look at that. Okay, so you need to do the orbital notation to see if you have any unpaired electrons. So why would it be attracted to an external magnetic field? Because keep in mind, what's going on when you have just an arrow going up? By itself, it has a magnetic field. Remember what we said earlier about coiled wire? You put electricity through it, it's going to create a magnetic field. I call it the right hand rule, that your fingers wrap around the direction of the coil and your thumb points up to the North Pole. So if you have an unpaired electron, it creates a magnetic field. Therefore, it's going to be attracted to another magnetic field. Okay, but what happens then if you have what's called a diamagnetic atom or ion? Okay, they're all paired up, so therefore nothing's canceling each other out. So if you have all paired up electrons, the north and the south, here's like your north pole and this like your south pole, they're going to cancel each other out, so it will be unattracted to a magnetic field. So it says look at the orbital notation for silver. Okay, what's happening here when I had silver, not the silver atom, excuse me, the silver ion, the silver atom. Right here, that silver atom has an unpaired electron, therefore it's paramagnetic. If I looked at plain old zinc, let's go ahead and do zinc. Zinc has an atomic number of 30, so we need to place 30 electrons. Let's go ahead and do the shortcut notation because I don't want to spend a whole lot of time writing everything out. So it's argon, 4s2, 3d10. So here is zinc, and if I were to do the orbital notation, here's my 4s. Hey, how many lines, how many dashes do I write for D? Do you remember? If you said 5, you're good. 3d. And there you have your zinc atom, your neutral atom. And yes, they're all paired up. There is no magnetic field being created, so it is not attracted to it. Even your zinc ion, do you remember what we said? What is zinc's charge always? Always, always, without any exception, it's going to be +2. Why? Because which electrons am I going to remove? I'm going to remove these guys. So I end up with argon 3d10. And if you want to do a quick check, argon has an atomic number of 18. 18 plus 10 is 28 electrons. You still have 30 protons for a charge of +2. If we were to go ahead and do this, and notice they're all paired up. So here we have zinc and zinc ion both being diamagnetic because you have all paired electrons, nothing is unpaired, so it does not have a magnetic pull to it. So let's go ahead and why don't you at least do the first couple of these, and I will do Fe+3 with you. So go ahead and do 1 and 2 and see how you do. Okay, so there's the first two for you. There's, and I decided to use the shortcut just to save us a little bit of time here. So you notice that the sulfide ion has 18 electrons, sulfur has 16 protons, and I added the 2 electrons. So if I want to see, well, which 2 did I add? I gained those 2. Is it diamagnetic or paramagnetic? It is diamagnetic because everything is filled up. Every electron is paired. For the iron +2, again, remember what I said, when you take away electrons, I'm going to take away the s electrons there. So you just leave argon with a 3d6. Once again, if you count how many argon has, is 18 plus 6 is 24. That's how many I have here. And here's your 3d6. So what is this going to be? Well, it sure is not diamagnetic because I see 4 unpaired electrons, so it's paramagnetic. Which brings us to an interesting case with the Fe3+. Very, very similar to Fe2+, but take a wild stab why Fe3+ exists. If I were to do this, you have argon 3d5, And look what's going to come off. This is what you have. Remember what we said, there is great stability with a half-filled a half-filled orbital there. So that works out great. I'm about out of time. You're going to have to listen to part 2. So go ahead and work on 4 and 5 on your own and then tune into the next one.